So, we have been discussing the various aspects related to Schottky barrier. We have seen what are the factors which affect the barrier height, what are the factors which affect the built-in potential, ideal, non-ideal characteristics, IV characteristics, all those we have discussed. Now, we are ready to use it in a 3-terminal device. So, the 3-terminal device, which is very popular with 3,5 compounds, particularly gallium arsenide, gallium nitride, all those substrates where the wide band gap is there, where it becomes more and more difficult to make p-n junctions, they use metal semiconductor MESFET, metal semiconductor field effect transistor, ME standing for metal, S for semiconductor, field effect transistor. So, we will discuss how it operates, what is the operation of this device and how do the IV characteristics look like. In fact, this will be similar or almost same as that of the junction field effect transistor. So, if you see, this is the structure of the metal semiconductor field effect transistor. Now, using the gallium arsenide as the substrate, because that is very popular with the gallium arsenide integrated circuits. So, integrated circuits have been realized with this approach. Semi insulating gallium arsenide, on that you have a N region, and this N region can be either realized by epitaxial technique or by implanting onto this semi insulating substrate. So, there is a layer which is doped with usually silicon or sulfur, that is the donors. Now, you have got here this red or this region as the source, that is ohmic contact, and the drain, that is also ohmic contact. When you say it is ohmic contact, you understand what it is now. It is gold germanium alloyed onto that contact N-type region, that makes the ohmic contact. So, straight away evaporate gold germanium, alloy at 400 degree centigrade for about a minute, you get the ohmic contact. We will have occasion to get into more into the technology details later, and this portion is actually the metal semiconductor contact, which actually should be rectifying contact, because you need to control the region below this. Ohmic contact does not have any effect below that, it only allows the current to flow in either direction with minimum voltage drop, whereas you need a rectifying contact. That means, below this metal contact there will be a depletion layer, and the extent of depletion layer will depend upon what is the voltage that is applied to this. And if this metal semiconductor, that is, if you apply a plus voltage with respect to the source ohmic contact, that is a forward bias junction. If I apply reverse bias, that is VGS is negative, that will be a reverse bias junction. So, I am just using the term VGS, if I VGS actually is positive if it is forward bias. Please understand this terminology. Gate to source potential is positive if it is forward bias. Gate to source potential is negative, the applied voltage is negative with respect to source if it is reverse biased. When nothing is applied, when you shorted this, there will be a built-in potential across this metal semiconductor junction. So, all that you have now is an insulating layer which does not do anything, it is a mechanical support, a N-type layer with 2 contacts at this point and at this point, from here to there. So, you can say that the contact is current collection begins from this end, current injection from this end. So, this is the source, this is the drain. Usual term for as MOSFET, source is the source of electrons, drain is the drain for electrons. Current flow will be in this direction if I apply voltage between the drain and the source. Now, let us take a look at the how it will operate. I will just draw this particular diagram there. So, suppose I have a bar of semiconductor N type. I put a contact here. This is the source, this is the drain. Okay. Now, if the voltages are low, when I apply VDS, if I apply VDS, this is N type, there will be current flow like this. I can call it as ID. There will be current flow from the that side ID, and I am applying VDS, plus there, minus there. This is like a bar of semiconductor. Voltage of VDS will be equal to ID into the resistance, simple, Ohm's law. So, VDS will be ID into R, where R will be the resistance of this region. If this depth is W, if that depth, okay, this is a cross section, W is the depth perpendicular to the board, if the depth is W, then R is actually equal to this. I can put it as, just rewrite it over here, ID into R equal to VDS, which is actually equal to ID into rho L divided by area. That is all what we are telling you. Rho is the resistance, resistivity. L is the length between the two contacts, okay, and A is the area of cross section. And area of cross section will be, if this is A, okay, area will be actually be equal to W into A, where W is actually the depth. In fact, you can call it as, if I call this as a channel length of length L, okay, if I call this as L, total length L, L is the length between the two, and W is the depth. Just remove it from here, put it as N, that is W. Okay. And of course, here you will have this coming like that. It is a bar of semiconductor. So, if I have a bar of semiconductor like that, it does not serve any purpose for us. Finally, what we want is, I must be able to vary this current. I must be able to vary this current using another terminal. Simple way is, if I can vary this current, okay, this will have a characteristic like this. VDS versus ID will be like that. The slope of that is the resistance. You know, this device is so simple to understand. All that you need to know is Ohm's law and apply it properly. That is all what you need to know. So, okay, that is the characteristics. I want to change this current. Supposing I want to reduce the current, okay, what should I do? I have to, if I can reduce the thickness of this layer, let us say you have a way of electronically etching that layer, remove this layer, the thickness A, if can be reduced by some height, this you will get another slope which is like this, A1, A2, okay, and A2 will be less than A1. Okay. A2 is less than A1. Okay. This is actually the understanding that you have got when you take area reduction. Now, the same can be achieved, you must be able to achieve it electronically. The area of cross section, that is the thickness of the channel, you must be able to reduce. That is done by applying the voltage to the gate. Now, what I have shown here is the same structure, whatever we have put on the board, except if you are putting the contact right here at this edge. Okay. I have not shown the gate, I have shown this length L. Okay. This is the L, and here if I go, this is the L. We are telling that you do not put physically the contact there, you put it slightly away from that, because you do not want to short this gate to this source region. So, there must be a separation between the two regions. So, what you will have will be a contact will be put here like this. That is a contact on the top that you have put. And we are in our first analysis, what we will do is we will neglect the drop across that, neglect the drop across that. What is the meaning of that? It is as if the contact is put here. All that we are saying is whatever VDS you are applying is practically appearing across that. You can do that by putting n plus contact here. You can have n plus region from here to here, then it is as if shifting this contact to this portion. So, in the this is what we are doing is Shockley's analysis. Shockley first gave in 1950, okay, way back, that was given where the contact is, even though it is there, you neglect the drop here, you neglect the drop here. Now, due to this metal semiconductor contact, what do you have below that? See, this height, thickness of this n layer, I put it as A, similar to what we put there, okay, and the depth of that into this plane, we have taken it as W. In all the analysis, we will do that, and this n region we call it as a channel, because the region in which the current flows. So, channel length is L from that end, the channel length is L, same terminology that is used in the case of MOSFET. Channel depth is or width is W and channel thickness is A. It is this A that you are controlling by applying voltage to the gate and source. Supposing I short the gate to the source, 0 voltage between the gate and source. What is the channel thickness? It is A minus this depletion layer width. What I put here is H. H is the depletion layer width, and the depletion layer width is related to the built-in potential now. Okay. Now, let us go into this discussion a little bit more carefully. So, the depletion layer width, we are considering VGS equal to 0, okay. Then potential drop across the depletion layer is equal to VBI. Depletion layer width is H. Okay. Let us just remove that VBI. There is a depletion layer width. Okay. Now, if a bias VGS is applied, then voltage or the potential drop is equal to this. I would like you to watch carefully. You can put the numbers onto that, but in analysis what we will put it as VBI minus VGS. Look, if VGS is positive, it is forward biased, the total potential will be VBI minus V minus that V forward bias. If VGS is minus VR, that is reverse biased, it will be VBI plus VR. So, you do not have to say anything, all that you do is put VGS, put plus 0.5 or minus 0.5. If I put plus 0.5, this is VBI minus 0.5, that is forward bias. If it is minus 0.5, reverse bias by minus 0.5 volts, it is VBI plus 0.5. That is all what you have to remember. So, please remember there is no confusion. So, consistently we will use VGS as the gate to source voltage, and the polarity is shown with gate positive. The applied voltage is reversed, you put it as negative. Okay. So, in equations we will always put like this. Now, let us take a look at the term. Okay. I will go back to this now. Depletion layer width depletion layer width is H. That is related to how much is the potential across the depletion layer. So, therefore, VBI minus VGS is the potential, total potential. You do not have to worry whether it is reverse bias or positive bias. All that you do is give a proper sign to VGS. VGS is positive, it is forward bias, VGS is negative, it adds on to that. I am repeating so that Q and D H squared that is the depletion approximation. Please remember, we are using only this equation in the analysis completely, because if you want to find what is the channel thickness now A, originally it was A, now it has been reduced by some amount H. Okay. You go back to this slide here, see here, the original channel thickness is A, it is reduced by this depletion layer width, because out of this portion thickness A, this entire thickness H is occupied by the depletion layer, no mobile carriers are there. So, conduction takes place only through this layer. It is as if you have removed that layer. As far as the drain source region is concerned or the channel is concerned, as if you etched out that portion, but it is there physically, you have removed the electrons. So, this is an insulating layer virtually, okay, and the conduction takes place through this layer. So, channel thickness now is A minus H. So, that is the width, okay, and H depends upon that quantity. Now, you can see if VGS is negative, this increases, that H increases. So, H will actually be equal to, I think I have got those equations in the slide probably. So, we will see. Okay. So, H can be related from this equation. All that we have to do is what is the voltage and what is the depletion layer height. You do that, subtract it from the channel thickness A, you get the area of cross section for current flow. Then use that equation VDS is equal to ID into R, where R is a variable quantity. R you are varying by applying gate voltage, that is all. That simple as that. So, all the symbols are clear. The ID is the drain current which will flow through this channel, and notice that depletion layer width is uniform everywhere. It is uniform everywhere, implying the potential drop across the depletion layer is same here, 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 or at least there is not much difference between the potential drop across the depletion layer at this source end and at the drain end. That means a drop in this direction is negligible. That is what is written here. The drain to source, in fact, when we say drain to source for the VDS, what we are considering is from this edge to this edge, that is the active region. When we write all the equations, we are writing equation when we say VDS, it is just across the channel length. We are not considering the drops beyond that point. That you can add as IR drop, because this portion thickness is not changing. It is a constant resistance that you can add up later if you want to. Other, and if you bring in this contact closer and closer to this, the drop becomes smaller. This aspect we will see later, how to bring it closer together and what impact it has on the IV characteristics, that has to be seen in the practical device. This is the problem that people faced with when making the MESFET and gallium arsenide initially, because in the case of MOSFET, you have self-aligned structures, whether you can get self-aligned structures in this device. So, our analysis really holds good for a self-aligned structure, in the sense n plus coming very close up to this point. So, we imagine that this contact is close to this point. Okay? With that understanding, and also with the understanding that initially what we take is VDS drop from here to here is very small compared to VBA minus VGS. What is VBA minus VGS? The drop here, drop from this point to this point. This, okay? And you want to operate this device with VGS positive, okay? Because that may start conducting. We will see whether we can do that later. So, in other words, what you are telling is, if VGS is 0, channel thickness is maximum, that is depletion layer width is minimum. As you keep on increasing the VGS, reverse bias negatively, the depletion layer keeps on widening. Okay? So, channel thickness becomes smaller and smaller, resistance becomes more and more, current becomes smaller. Okay, so, with that let us see now. These symbols should be clear to you: H, A, ID, VDS, etc., and L is the channel length, depth is W. Now, you see that we have rewritten that equation what I wrote initially. VDS now, Ohm's law. I say linear region because that is the region where VDS is very small compared to that. Okay? And when we say linear, ID VD characteristic will be linear. So, if you satisfy this condition, this whole region from here to here is a fixed resistor of height A minus H. H is constant right through. So, VDS is equal to ID into rho L by A. L is the channel length, rho is the resistance of the n layer, A is the area of cross section. Now, you see substitute. It is much simpler compared to the MESFET. Okay. In fact, even circuit engineers enjoy writing these equations because it is all that is there. So, rho is 1 by q n d mu n, that is rho, the first term. Okay. That is the first term, which is the rho. This is sigma, q n d mu n is sigma, 1 by sigma is rho. And okay, area of cross section, depth, see here, area of cross section is this height, which is h equal to A minus h. A minus h is the channel thickness. Now, depth is W. So, W into A minus h is the area of cross section, L is the length. So, VDS is equal to ID into rho into L by A. Okay. So, now I put ID is equal to VDS into this whole thing goes up to numerator. I just put it in terms of ID now. ID is equal to Q n d mu n W taken on that side. I pull this A out and within bracket you get 1 minus h by A. Okay. I have just rewritten that. All that I did, if you have difficulty, I will just put it back on the board. So, VDS is 1 by q n d mu n, that is rho, 1 by that is rho, okay, into L divided by area W into A minus h into ID. This is whole thing is R. Okay, therefore, ID is actually equal to q n d mu n into W into A minus h divided by L into VDS. Okay. What I did is I pulled out this A and you get Q n d mu n W into A divided by L into 1 minus h by A into VDS. What is this term? This quantity is nothing but 1 by rho sigma into area by L. I just put that whole term, this particular term, as sigma into area of the full channel. If there is no depletion layer, the channel thickness is A and depth is W. W into A is the cross section of that entire resistor. Okay. Let me just go back and show you. See, if there is no depletion layer, that is A and that is L, depth is W. So, rho into L divided by W into A. Okay, that is channel resistance, and I put it as channel conductance 1 by that. So, sigma into area by L, that is G naught. G naught is that quantity. I am writing that because it works out easy to write that one alone, instead of writing all these right through. If there is no depletion layer, channel resistance would have been 1 by G naught, but it is never that much, it is always higher than that, because it is not A, it is always less than A because of depletion layer. Okay. So, once you have got this, you should be able to write what is H, what is C. Okay. Now, for that we define one particular term now. So, you got the relationship between I D and V D S. Here all these are constants. Here this is a constant, A is a constant, once you decide the thickness of the P layer. H, it is a constant for a given V G S. Okay. So, whole thing is a constant for a given V G S, this whole thing is a constant. So, you will get actually a characteristic I D proportional to V D S for a given V G S, and I can get similar characteristics for by varying V G S. Okay. Now, just write A, instead of writing it A, it becomes easier to define a term called pinch off voltage. Okay. Now, let us just go into this one or two things I want to write here. This is the equation that we have got. Okay. This is the equation you have got. We have seen that H is equal to, we have seen V B I minus V G S is the total potential across the depletion layer, which actually is equal to, I think I should retain this term, correct. So, H is actually equal to root of twice epsilon r epsilon 0 V B I minus V G S divided by, this is a complete depletion approximation. Okay. You have got, this is a H term. Now, you define a term called pinch off voltage. I want H by A ratio here. H is related to the related to V G S. If I increase V G S reverse bias more and more, that term goes on increasing. Okay. Now, I define a term, okay, what is known as pinch off voltage. Let us see. Depletion layer width H depends on the potential across the gate V B I minus V G S. Applying abrupt junction model, that is what you have written there, twice epsilon r epsilon 0 divided minus V G S by Q and D. So, always you remember this equation again and again, I will be using it here. Best thing to remember is H is proportional to square root of V B I minus V G S, because now we define a term called pinch off voltage, where depletion layer H becomes equal to A. Okay. We define the pinch off voltage as the potential drop across the depletion layer required to make H equal to A. The channel is fully pinched off, completely depleted. and the current will be 0. If the depletion layer completely goes over totally, okay, then the current will be 0. This potential is termed as the pinch off voltage V p 0. Okay. I will just go back to this once to see the thing. You are finding out how much should be the potential drop across the junction, so that the depletion layer completely comes this all the way up to this insulating layer. So, it is closing down entirely. There are no carriers present anywhere in that region. Between the source and drain, complete layer is depleted. So, what is the potential across that? Not the applied voltage. What is the potential across the depletion layer, so that the depletion layer, the channel is completely depleted. That is what we call it as pinch off voltage. Okay. Now, that will be that. Okay. This is related to H. I am replacing this by A and defining the total potential. Instead of V b I minus V g s, I have got V p 0. It is not applied voltage. It will include the applied voltage also. Okay. It may be depleted at 0 bias also, depending upon thickness. So, V p 0 is H is replaced by A. That is all. How much is the potential drop across the junction or the Schottky junction to make the depletion layer equal to A. Okay. Now, that means you can write instead of H equal to is proportional V b I minus V b s, A is proportional to square root of V p 0. So, that is the same equation. When we wrote H here, when we wrote H, the V p 0 is equal to is replaced by V b I minus V g s. Now, therefore, substituting H and A in I d, so we got the term G naught into 1 minus H by A V d s. So, I substitute for H and A. What is H divided by A? Okay. So, H is this, and A is actually equal to square root of twice epsilon r epsilon 0 into V p 0 by Q and D. So, H divided by A is actually equal to square root of the potentials, all these things cancel. So, H divided by A is square root of V b I minus V g s divided by V p 0. That is it. All that you have done is substituted for H and A. So, G naught into 1 minus H by A into V d s is the IV characteristics, that is that. Now, you can see clearly why we wrote V p 0, because V p 0 is fixed for a device. V p 0 is fixed for a device whose thickness and doping are fixed. When you fix the device, doping and thickness are fixed. So, V p 0 is fixed. That is why you write it in terms of V p 0, pinch off voltage, and this comes handy in while analyzing the device characteristic later. Okay. Now, you can see here, this is linear characteristics for a given V g s. I d and V d s are linear for a given V g s. Go back to this, V g s equal to 0, it is 1 minus V b I by V p 0 square root of into V d s. Okay. If I increase the V g s reverse bias, this V b I plus that reverse bias quantity. So, V g s equal to 0. I am taking a typical case where V b I is 0.8 volts, the volt is missing there, 0.8 volts, V p 0 is 4 volts, okay. V p 0 is 4 volts. So, if V b I is 0.8 volts, when V g s equal to minus 3.2 volts reverse bias, the total quantity will be equal to this is 0.8 volts VBI, okay, and this is minus 3.2. So, 0.8 minus 3.2, that is 4 volts. So, when the VBI minus VG is equal to 4 volts, you have got a potential drop across the channel equal to Vp 0. What is the current at that point? That is very small. I just showed still small current, virtually everything is gone down. There may be small leakage current will be there, just I did not show it as 0, but virtually it will be 0. This is almost flat. This is when the VGS is reverse bias so much that the channel is depleted fully all the way. So, from 0 you keep on increasing reverse bias, minus 1, minus 2, minus 3, minus 3.2, you are able to shut off the transistor completely. The device conduction is made 0. So, that is the using this equation you can really find the slope of this. Okay. Circuit engineers, okay. The circuit engineers use this behavior in many places in circuit applications. Okay. Many linear circuit. Okay. I am sure some of the people who teach that would have been talking about that. One of the very popular applications is in a Wien-Bridge oscillator. Okay. Wien-Bridge oscillator, what do you have? Just leaving this, because as electrical engineer we would like to take a look at that also. Just a very good example is when you make a Wien-Bridge oscillator, it is an amplifier of gain 3 with RC combination as in the feedback circuit. Okay. So, just let me draw that quickly, so that as a recapitulation for the memory. See, if you have a simple amplifier circuit, you will put an op amp, R1, R2. The ratio is so such that, say for example, this is V naught, this is V in V1, okay. V naught into R2 divided by R1 plus R2. That is the voltage here, that is equal to that is equal to V n. So, you have got A is equal to V naught by V 1, which is nothing but 1 plus R 1 plus by R 2. 1 plus R 1 by R 2, I think you have been tired of listening to this probably. 1 plus R 1 by R 2 is 3. That means, R 1 by R 2 is equal to 2. You make this 2 compared to that is 3. And then what do you have? Wien-Bridge. Okay. You have here, just for completeness sake I am drawing capacitor here, R C, and then I am drawing to the purpose and connect this to feedback. That is the Wien-Bridge oscillator. R C, everything you have a frequency of oscillation equal to 1 by 2 pi R C. But what will be the amplitude of this? You have no control. You put on the power supply to this op amp, it will turn on, you will see the amplitude goes on building up. What is the limiting factor here? It finally is limited by nonlinearities. The nonlinearities when they set in, okay, it is less than supply voltage, some value it will take up. But now, I want actually precisely, let us say 3 volts at the output peak. What will you do? You must have this resistor adjusted such that only for that output voltage, the gain becomes equal to 3. So, what do you do? Put a variable resistor here, okay, and this whole thing as R2. This resistance you adjust such that when this R1 divided by R2 is equal to 3, you get that amplitude. How do you do that? Take the output from here. Okay. So, what you do is, it is out of my syllabus, but still what you do is you connect it to a simple arrangement to the JFET. This is N channel, the JFET. This is the resistance. This resistance is a variable resistance. The resistance can be varied by varying the gate voltage. Depending upon what is the gate voltage, you get this resistance. Okay? So, you have to the output voltage, whatever be the voltage, this value will be only, this will oscillate only when R 1 by R 2 is equal to 2. That is, only when the total value becomes half of that. If the output goes up, what happens? If the output goes up, VGS goes up. So, you shift from one curve to another curve. Okay? You can connect it such that it gets reverse biased or forward biased. You can get the output negative, if you get, it will be reverse biased. Okay? So, you have a, it can be JFET or a MESFET. So, if the, you can adjust the gate voltage. See, this will work as an oscillator only if this resistance is equal to R 1 by 2. That means, only when this resistance has a particular value, supposing this is 2 k, this should be 1 k, and if I put this as half k, only when this becomes half k, it will work as oscillator. This will be half k only when a particular gate voltage, okay, and only for a particular output voltage. In fact, you must have a rectifier in between here. Okay, you need a rectifier here, because to give input to this gate, you can get, this should be DC, what you get here is the AC. So, a rectifier, you can have an inverter if you like, so that the polarity is reversed and you can adjust that voltage. So, what is this voltage depends on what the voltage here is, and only when it becomes 0.5 k, for in this example that I have taken 2 k, 1 k. So, this should be half k, let us say if it is half k. So, when this becomes half k, this becomes half k only for a particular gate voltage. That voltage decided by the output voltage. So, what happens is, I am sure you have done, some of you must have done this experiment in the laboratory. So, what happens is, only for a particular voltage it has a gain of 3 output voltage. That means, actually it will work as an oscillator with a fixed amplitude stabilized Wien Bridge oscillator. Okay. This is just off the discussion. This is what you call it as amplitude stabilized. Okay, Wien Bridge. Oscillator. Okay. I just thought it is better to see what some of the applications are right away here. They are very popular applications, whether you are at undergraduate or using it somewhere. It can be JFET, it can be MESFET, it can even be MOSFET. Okay, even MOSFET can be used because it has a linear region. So, this is one application. There are several other applications one can think of. Now, let us see what happens if I keep on increasing the VDS. As VDS becomes larger, what happens? See, remember this particular analysis we have done, I am going back to that. I do not have to go to that. This particular analysis we have done for the case VDS is small compared to VBA minus VGS. Please recall that. So, as VDS is increased, it will become comparable to VBA minus VGS. It can even become larger. So, let us see what happens. So, as VDS becomes larger and comparable to VBA minus VGS, the potential drop across the depletion layer increases from VBA minus VGS to VBA minus VGS plus VDS. As we move from the source end of the channel to its drain end. Okay, let us see what is the meaning of that. At the source end, what we are telling is, you cannot neglect this drop compared to the depletion layer voltage drop. In the linear region, the drop from drain to source, that is across this channel length, is small compared to V b I minus V g s. So, V b I minus V g s is the drop here, I have just put it here. Okay. Now, if the drop in this direction is negligible, what will happen to depletion layer width? Same. If this drop is negligible, the potential drop here and here will be same thing. Now, if the drop becomes comparable to that, this drop, as you move from this end to this end, the drop across depletion layer becomes more and more. It is understood? If you do not understand, I just because this is where some difficulty can be there. Take the case where it is easy to understand the situation where V g s, I do not even have to show the semi insulating layer, because it is only this layer which matters. Drain and this is the source. Okay. So, what you are telling is, let us say V g s is 0. Okay. And if V d s is small, I have this depletion layer like this. Okay. This is the situation when V d s is small. That is, drop in this direction is negligible. And what is the potential drop across this here now? Built in potential. From here to here, there is no voltage V g s. So, at this point it is V b I. And if this drop is negligible, this is also equal to V b I. Okay. Now, if there is a drop like this here, V d s, what is the potential here? I am neglecting this drop here. Okay. This is negligible. So, this is same potential here. Okay. So, this is plus, this is minus, built in potential. Built in potential polarity is plus minus here, plus minus here. Now, if I move from here to here, what is the potential from here to this point? That is what we are trying to see. From here to that point, in this region it is only V b I. In this region it is actually equal to V b I, see, is minus plus and this drop also is there, okay, minus plus. So, you have got additional drop coming up, this minus, this region plus, this adds on to that. Okay. So, you have got minus plus here, you have got another minus plus coming up here. So, total potential drop from here is, see, you have one drop here, another drop in this direction. This drop adds on to that. Okay. So, you have got a voltage drop which is actually equal to V b I plus V d s here. Okay. So, what happens is, as a result of that, that is what I plotted here. The depletion layer here becomes wider. Here it is V b I if it is 0, here it is V b I plus V d s. At any point here, it is V b I plus V of x. Okay. I hope that point is clear enough. It is just adds on to the depletion layer potential. Across the depletion layer, it is addition. It is just like taking a p n junction, applying extra voltage across that. Okay. See, plus minus, you are applying another plus minus across that. Plus minus, this is adding on to that. Plus minus, plus minus. Let us say put this example. You take a p n junction into the barrier, you add on potential if you reverse bias it. So, this is the potential, this you connect to that, it is as if you applied this voltage across that, additional. So, built in potential plus V d s comes in there. If you take any point here, if this is V of x, the potential drop here is equal to V b I plus V of x. Okay. In general, if I apply V g s to the gate, the potential drop across the source region is equal to P b I minus V g s, and at this point it is equal to V b I minus V g s plus V of x, and at this point it is equal to V b I minus V g s plus V d s. We are neglecting that drop. Okay. So, there is one simplification which Shockley did. What Shockley did is, one thing is that total depletion approximation, that we have already made use of. What is the meaning of total depletion approximation or deep depletion approximation? Voltage is related to depletion layer charge by that equation, square equation. The other thing is, you can see that the channel now gradually decreases in height, and when we wrote, if we can write the expression for depletion layer width here by subtracting total height A minus h, and h we can write it as equal to square root of twice epsilon epsilon 0 into the potential across that divided by q and d. Okay, you have to remember this. See, the h at any point can be written as square root of twice epsilon r epsilon 0 into whatever potential we wrote this last time, but now what you have got is plus g of x, the drop that comes up, divided by q and d. Please remember, if you write an expression for h, the channel thickness is A minus h, and current and voltage are related by V is equal to I into R. R is that thickness. That is all what you are trying to find out again. Only difference now is, you have got this channel thickness not constant right through, but it is falling. Now, when we write this equation, what is the meaning of that? The meaning of that is, the electric field here in this direction, it is totally in this direction. If I call it as y and that is as x, perpendicular to the channel is y, parallel is x. So, what we assume is, even though there is a field in this direction because of the VDS, that field is negligible compared to the field in the y direction. That is the assumption that we make. Then only we can write this equation strictly, because electric field is completely one dimensional in that direction. That is called gradual channel approximation. So, the gradual channel approximation is the famous jargon that is put up by all device physicists, meaning the electric field in the x direction is negligible compared to the y direction electric field. So, you can use one dimensional equations for writing the relation between depletion layer width and the potential across the depletion layer. That is what is done. Thickness of the channel reduces gradually from source to drain. We assume that electric field in the depletion layer is one dimensional in the y direction. Okay? This is referred to as gradual channel approximation. That was what Shockley did, very clever thing at the time. If I started with two dimensional analysis, I think nobody would have understood the JFET or MESFET. Okay? So, that is the point. Now, assuming that Ohm's law holds good, the voltage of dV across the length d of x can be written as follows. How do you write? V is equal to I into R. Delta V is equal to I d into resistance of the thickness. So, what we are writing now, go back to this, what you are writing now is the resistance of that region and drop in that region. dV is I d into the resistance of that region. I d is constant right through, because after all what current flows here will then come out here, it is continuous. I d into R. So, what we do is dV, the voltage drop across that region thickness, is given by I d into R of that d of x length, that is given as d of x divided by this quantity, that is actually 1 by q and d mu n is rho, I d into rho d of x divided by area of cross section. Area of cross section now is actually W into channel thickness. Channel thickness is A minus H. Okay? That is potential dependent. So, we use this integrating, we get the total drop. All that we do is integrate that, and once we integrate that, what we do is substitute for h here, okay, that term. H is given by this term. So, it is a voltage dependent term. So, what you do is, I will continue on this in my next lecture, because it is time now. So, what we do is, when you integrate it, what sort of terms we get. So, today we have seen that we get the linear characteristics, but we will see now that it will deviate from linearity if you include the drop in the y direction. If you include the V d s or V of x, that part we will discuss in our next lecture, taking this, completing the integral into account. Okay, we will see you tomorrow.